In our last lecture, we have introduced the concept of zero of a nonlinear function. Let us just briefly review what we have done on this topic and then proceed from there. We are considering an equation in one variable f(x) is equal to 0. This function is either a polynomial of this particular form, or it could be a transcendental function, which will be a combination of polynomials, exponential functions, trigonometric functions, logarithmic functions. We are interested in finding the zeros of such a polynomial or a transcendental function that is given to us. We have defined a zero or a root of a function f(x) as any value x is equal to xi which satisfies the equation automatically, so that f(x) is equal to fy is equal to 0. Now, we would like to distinguish between a simple root and a multiple root of a given polynomial or a transcendental function. If x is equal to xi is a simple root, then f of xi is 0, but its derivative f dash of xi is not equal to 0. Now, as we gave an example, x is equal to 1 and 2 are simple roots of this equation, a polynomial equation which can be factorized as x minus 1 into x minus 2. Similarly, if we have a root of multiplicity m, then derivatives up to order m minus 1 are 0 and mth derivative at xi is not equal to 0. Then we shall say it is a root of multiplicity m, and if we set m is equal to 1, we go back to the simple root that it is a f of xi is 0, f prime of xi is not equal to 0. Now, if it is a root of multiplicity m, theoretically it is possible for us to factorize it and get the factor out. That means I can write down f x minus xi to the power of m into gx is 0, g xi is not equal to 0. This may not always be possible to do for a transcendental function, because it is not possible to write the common factor and write it, but for a polynomial, yes, we can do it. But theoretically it would be possible for us to write it in the form of f(x) is equal to x minus xi to the power of m and gx is equal to 0. We also gave an alternative definition for defining a multiple root, so that if you have a method to obtain a simple root, the same method could be used if we are able to construct a new function which also has a simple root. So, with that concept, to use that concept, we know that if f(x) has a root xi of multiplicity m, then its derivative has the same root xi but of multiplicity m minus 1. So that if I now consider the ratio of these functions, these two functions, that is f(x) and f prime x, if I consider this ratio, then hx has a simple root xi. Now, as I was saying earlier, if I am able to construct methods which gives me the simple root much more easily, then I can use to find the multiple root also and apply the same method on the function hx, so that I will get the simple root of hx and hence the multiple root of f(x) is equal to 0. As an example, we give this as the multiple root of multiplicity 3, so that I am able to factorize it and then take x minus 2 whole cubed outside. Now, what is it that we are really looking for? We are talking of 0 or a root of an equation, and what do we really mean by that one? What it means is that if I have if I draw the graph of this function y is equal to f(x), then either the graph is cutting the x axis like this or it is cutting the x axis like this. We are interested in finding that value which is the point of intersection of the axis with the graph of the y is equal to f(x). Now, if you want to construct methods for this, there are two types of methods. One is called the direct methods, the other is the iterative methods. In the direct methods, we can produce a solution in a finite number of steps. Therefore, that means we will be able to count total number of operations in a particular method and say you need to do this many multiplications, this many divisions, this many additions and subtractions. Now, usually when you are giving an operational count, the total count, we normally give the major operations, that is the multiplications and divisions, and the minor operations are additions and subtractions. We know that addition subtraction takes much less than the multiplication and the divisions. Sometimes we include all the four, but very often operational count would mean the major operations. Now, in an iterative method, we use the idea of successive approximation to a root. What we mean here is that we start with an initial approximation, we will get the initial approximation through some other way, and then starting with that initial approximation, we shall now proceed to find the sequence of approximations x1, x2, x3, and which we hope it will converge to the exact root of the solution. When it will converge, when it will not converge, we will look at it. Now in the example that we have just now given, the polynomial a naught x square plus a1 x plus a2 is equal to 0, if I straight away solve this and write it in this particular form, then this will, I shall call this as a direct method. I am able to write down the solution of the problem in just one step. If I want both the roots, 2 steps. Now as I said last time that we will be able to count the total number of multiplications. Here there are number of 3 multiplications, as we have counted here there are 2 for this one. A square can be taken as a1 into a1. So I have got here 3 multiplications, I have a division here and I have got a addition here and an addition here. So there are 2 additions that are coming into picture here and 1 square root. So I am able to give the total operational count for this, so that I will be able to tell what will be the total amount of computed time that a method can take. So I can multiply the, if I given the time factor for multiplication and division, and suitably I can multiply that and then say this is the total amount of computed time that this method will take for this solving this particular problem. Now if I take the example of this a naught x square plus a1 x plus is equal to a2, I can write down a number of iterative methods. Which one of them would converge, we do not know. We have to do the convergence analysis of this and see which one would converge, which one will diverge. For example, as we discussed last time, let us repeat it again. For example, for the simple trivial equation, what I have done here is I have taken these 2 terms a1x plus a2 to the right hand side, then a naught x square is written as a naught x into x. So we have taken a naught x to the right hand side and then we constructed that this will be the new approximation and this will be the old approximations. So I now construct an iterative method of this particular form. Similarly in this case we have kept the middle term on the left hand side, the first and the third terms to the right hand side, and then written an iterative method over here. And in third case we have taken these 2 terms, taken x common out from here, and I have taken this a2 and this quantity to the denominator. So therefore this describes 3 iterative methods for solving the same problem, and all of them are the form xk plus 1 is equal to g of xk, so that the new approximation is here and the old approximation over here. As I mentioned, which one of these 2 will converge we will see later on. Now we have just now mentioned that what it gives us is an infinite sequence of approximations. Now it is very important for us to know, does this sequence converge at all? I mean, what is the convergence criteria, how we are going to impose it. Secondly, it is an infinite sequence of approximations. When do we stop this iteration? Because theoretically we are doing infinite cycles of computation, but we will have to terminate it at some stage, and termination stage could be that we say that we need this particular accuracy or some other things that should be given, so that the iteration can be terminated at some stage. Now what do we mean by convergence? Let us define it. By convergence we mean that we have a sequence of iterates xk, it converges to the exact root xi if we are taking infinite sequence. So limit k tending to infinity xk minus xi is equal to 0. Now I can define xk minus xi as error at any iteration, because this is the value that we are obtaining at a particular iteration, this is the exact root. So I can define this xk minus xi as error at any particular stage. Now during that iteration I can find out what is the magnitude of the error, and if the error goes to 0, as k tends to infinity, we are getting limit xk is equal to xi. That means we are now achieving convergence. Even though this is the test, we shall see how we are going to apply this. Now the second point is, when should we stop the iteration? Now the stopping criteria, or the criteria for that we have achieved a particular convergence, is let an accuracy epsilon be prescribed. So we can also use the word tolerance. Then if once you say that I want in a particular problem 5 plus accuracy I need, or 6 plus accuracy of the solution is required, so you have now prescribed the accuracy that you want in a problem. So then we can do any one of these criteria can be used. What we can do is we can say difference between 2 successive iterates. Now we are doing starting with x0 we got x1, got x2, we got x3. So I can find out the difference between these 2, any 2 starting at a particular stage. After few iterations we can start testing what is x3 minus x2 in magnitude, what is x4 minus x3 in magnitude. So, I can go on finding what is the in magnitude what is the difference between two successive iterates. If it is less than the tolerance that is given to us, then I can stop the iteration and then give you the output of the whatever output that is required. Alternatively, we can also stop the iteration procedure when the equation is satisfied to a certain accuracy. That means our equation is f(x) is equal to 0. So, if at a particular iterate xk plus 1, if I substitute f of xk plus 1, it should be say 10 to the power 6 accuracy. So, when once accuracy is prescribed, I can look at the equation itself and then see whether the equation has been satisfied correctly or not. Therefore, I can have this particular criteria also. Now, what does really this mean graphically? Let us just have a look at what it really means graphically. Now, I am describing here the first case here. I have taken the x axis and f(x) here. Now, this is the graph of this, xi is the exact root. Now, I have taken xk as a particular approximation. Now, the successive approximations move towards the exact root. So, I have got xk plus 1 as a new approximation, xk plus 1 minus xk I am testing it here. Now, as we proceed to successive iterations, this xk plus 1 would go on moving towards this, and the difference between two successive iterates at any particular stage is going to be less than epsilon. Whereas, in the second case we are finding what is the value of f of xk plus 1. F of xk plus 1 is nothing but fx, that is your ordinate. So, if I take a particular approximation xk plus 1, I am testing what is the value of this ordinate. As we move towards this root xk plus 1, this f of xk plus 1 goes to 0 and finally f of xi is exactly equal to 0. Therefore, here in this case we are testing the ordinate, whereas in this case we are testing the abscissa, that is the difference between two successive approximations is less than epsilon or not. Now, sometimes you may have to use both. The reason being, we would like to know when this criteria that we have written or this criteria may fail. It may fail. Let us take this graph completely. The first criteria may fail when the graph of fx cuts x axis almost vertically. Now, let us see what is going to happen. I have drawn the graph of this. Now, just draw the graph almost vertically to this. Then if I take any two successive points here, xk on the left, xk plus 1 on the right. So, these two are the points. Now, even though that they are very close to each other, since the graph is almost vertical, this f of xk or f of xk plus 1 will be very large. That means the equation fx is equal to 0 has not been satisfied correctly, because the graph is almost vertical. In that case, the first condition, that xk plus 1 minus xk in magnitude less than epsilon, would fail. And similarly, the second criteria would fail if the graph is cutting almost horizontally. So, the graph is falling like this and then cutting the x axis. You could see the reason why it is so. If I take any two successive approximations xk plus 1, when the graph is cutting horizontally, the f of xk plus 1 is almost 0, but the difference between xk and xk plus 1 will be very large. Now, look at the graph which can write almost tangentially to this one and cutting it. So, if you take the value of the ordinate is less than epsilon, but we are not getting the root because we are far away from the root, because it is cutting very horizontally. Of course, if you are going to test both of them together, there is no question of failure. If you want to use both the conditions together, then there is no question of failure in any particular case. However, in most of the cases we may not use both of them, hoping that it is not a typical case of one of these two cases, but the failure can obtain. That means when you are solving a particular problem and you have difficulty, that you may have to think that maybe a kind of the graph of the function is coming either horizontally or vertically. Therefore, we can use both the conditions together to avoid that particular pitfall. Now, the next step is that we said that I want an iterative method, but I want a starting approximation. Obtaining a starting approximation is very important, because suppose an equation has got a root at minus 10, root is minus 10. If I start an approximation at say plus 5 or plus 10, which is so far away from the root, it may not be possible for the iterative method to converge that root, because it is too far away from the root. Therefore, it is necessary that the approximation which we are talking of should be in the neighborhood of the root. Neighborhood does not mean a small very epsilon neighborhood, it is quite large, a reasonably large. Maybe the root, say root is lying minus 10, you may say the root is lying between minus 15 and minus 8, or root is lying between minus 15 and minus 5. So, a reasonably large interval is allowed, so that we need a suitable initial approximation. And in fact, in many cases the situation would become much worse if we have a system of nonlinear equations. Here we are talked of one variable problem, that is f(x) is equal to 0. If I take two variable problem as f(x y) is equal to 0, g(x y) is equal to 0, it is nonlinear in two variables. So, I need very good approximation for both the variables x and y. Therefore, this situation will become more important in the case of system of nonlinear equation, which is very commonly encountered in almost all your applications. Now, there are two ways of obtaining the initial approximation. One is the use of graphic method, the other is the use of intermediate value theorem. Let us see what we mean by the graphic method. In the graphic method, if I am able to draw the graph approximately, we are not talking of exactly drawing the graph. If I am able to draw the graph of x is equal to approximately, I can use it to get a initial approximation. So, draw the graph of it, let it cut the x axis at a particular point, and when it cuts the x axis at that point, I can take that as the required approximation or initial approximation for this. That means I have got a so what we are really saying is that take your axis, take the graph of this, substitute few values of this, because the f(x) could be a very complicated function. So, substitute few values, get the values, and then just plot rough graph of this, and then wherever it is intersecting that point, take your approximation as your x naught. So, we shall take that as the initial approximation for starting the iterative method. Once I have an initial approximation, I do not need anything else, the method itself will give me the successive approximations. Now, this is if we are not able to write or plot the graph of x is equal to 0, we can think of breaking the function f(x) is equal to 0 into two parts as f(1x) is equal to f(2x). That means I could write it, for example, write f(x) is equal to 0 in a convenient form as f(1x) is equal to f(2x). For example, if I want this graph, the approximation for x minus sin x is equal to 0, I can write this as x is equal to sin x, take f(1x) as x, f(2x) as sin x. So, I know the graph of f(1 y) is equal to x, I know the graph of y is equal to sin x. Now, wherever it approximately cuts it, I will take the approximation, that as my initial approximation. So, this is the idea behind. If you want to break this write f(x) is equal to 0 in the form of f(1x) is equal to f(2x), yes, we can break it like that, and then draw the graph of y is equal to f(1x), draw the graph of y is equal to f(2x). The point of intersection is a root. Any value close to this point is an approximation. So, approximately we are drawing the graph and getting the point of intersection and taking that as my approximation. But of course, it is not a practical method. We really strictly we are not going to use in our applications, because it is very difficult for us to draw the graph of this and try to get the initial approximation. Now, but let us illustrate how we are going to get the initial approximation. I take a simple example of f(x) is x square plus x minus 1 is 0. So, I want to get the initial approximation for this one. It is a quadratic equation, I know it represents a parabola. I will try to draw the graph of the parabola approximately. So, I can now write this y is equal to f(x), then make this as a perfect square x plus half whole square, and then add and subtract 1 by 4. So, I will get minus 1 by 4. So, I take this 5 by 4 to the left hand side. So, y plus 5 by 4 is equal to x plus half whole square. So, from this I can recognize that this is a parabola with the axis opening upwards. So, we can say that this is a parabola, vertex at minus half minus 5 by 4, and opening upwards because of the negative sign. And now I take x axis, y axis, draw the graph of this parabola. I know this is the vertex and draw approximately, just take 1 or 2 points here and then draw the graph of this, and then I have got the 2 points A and B. Depending on which route is required, the positive route is required, negative route is required, I can take the approximation accordingly. I can take this value as the for the positive route and this value as the negative route. So I can draw the graph of the y is equal to f x is equal to 0 in this form, or as I gave an example earlier, you can take the graph of y is equal to f1x and the graph of y is equal to f2x. But now let us discuss the other way of finding the initial approximation, which is the most useful and which one we shall use it often in our analysis, which is called intermediate value theorem. We assume of course f x is a continuous function in a b, and the f of a, f of b is less than 0. Then f x has at least one real root or an odd number of real roots in a b. Now what we are really saying here is f x is a continuous function on a b, f of a into f of b is less than 0. So or the graph need not be like this, it could be, it does not matter if it is cutting the other way around. Now you can see that f of a into f of b is negative, that means one of them is negative, other is positive. Therefore either f of a is negative here, this ordinate is negative, this ordinate is positive, or alternatively this ordinate is positive, this ordinate is negative. When the product of these two ordinates is negative, it has to cross the graph has to cross the x axis. Since the graph is crossing the x axis, we have located a root in that particular interval. Then f x has one real root or an odd number of real roots in the a b. Obviously I have taken a nice graph like this, but it is possible that the graph is cutting the x axis more than once. So it will be, then we will have the located more than one real roots. Therefore it will have one real root or an odd number of real roots, particularly when the roots are very close to each other, say 1 and 1.2, let us suppose were the roots of particular equation. You might have seen that the root lies between 0 and 2. So like that you will construct, but of course not correct, should say 3 roots, because it is going to be odd number of real roots. So there are 3 roots, 1, 1.2, 1.4, and you picked up the interval as 0 and 2. Therefore it will say that it has got at least one root in the interval, one or odd number of roots. So this way I can locate it, and once I locate it, I know that I should be, approximation should be good. That means the initial approximation should be close to the exact solution. Therefore if necessary I can refine, let us suppose you say that 0 is between 0 and 50. Now this interval is too large, I can reduce this interval further to test whether at 25, say 0 and 25 is the root is there, or 25 and 50 root is there. It is possible for me by using the intermediate value to reduce the length of the interval to any length which I want. Then I can go for a numerical method and construct the numerical method. See, let us take the simple example of the same one earlier, where f x is equal to x squared plus x minus 1 is 0. Now I would test few values, f of 0, substitute 0, I get minus 1, substitute f of 1, I get 1, substitute minus 1, I get 1 minus 1 is minus 1, f of minus 2, substitute it here, 4 minus 2 minus 1 is 0. Now I can see that f of 0 is negative, f of 1 is positive, f0 into f1 is negative, and again f of minus 2 minus 1, these are negative and positive, therefore its product is negative. Therefore I have located both the roots of this equation, one root lies between minus 2 and minus 1, the other root lies between 0 and 1. So I have now located the two roots where they are lying, and once I have this one, then immediately I can go to any iterative method, I can start the iteration procedure from there. Now therefore usually we can form a table of values to find the interval in which the root lies. Now here we are talking of you need more than one root. So, if you need more than one root, you can form a table of values, and if you say a polynomial of degree 5 is given and you want to find out where the roots are, all the 5 roots, if they are real, where they are existing, that you will be able to find by constructing a table of values. Now, when once we locate it that the root lies in a particular interval a b, now I would go for iterating it further. Now, the
f0 into f of minus 2, then also we will get less than 0. So can we say that there are
between 0
f of 0 into f of minus 2, that will also be less than 0.
Yes, there is obviously a root, because see this is minus 2 minus 1, there is a root between 0 and 1, right. Now you are now removing this and saying between minus 2 and 0, right. So trivially it is there, but what is the length of the interval minus 2 to 0? Length is 2, and the length of the interval minus 2 to minus 1 is 1, length is 1. Therefore this is a refined interval than minus 2 0. You are right, you can also take as the root lying between minus 2 and 0. But now when once I have given this is a smaller interval, length of the interval is 1, therefore I have given a refined interval in which the root lies. Yes, if we want to iterate a particular thing, this is okay, minus 2 to 0 can also be taken and we can proceed on, except that it may take one more iteration, extra iteration to get to the required accuracy of the problem. Now the simplest and the trivial method is bisection method. The bisection method is trivial because we apply the intermediate value theorem repeatedly, each time bisecting the interval. I mean that this example we just now he had asked the question, that is what he is saying, that he had asked the question that the root lies between minus 2 and 0. Yes, the root lies between minus 2 and 0, let us bisect it. The root bisection of minus 2 0 is point is minus 1. Now I will test whether the root lies between minus 2 and minus 1 or minus 1 and 0. Now I find that the root lies between minus 2 and minus 1. So given starting with a particular length of the interval, each time I will bisect the length of the interval and then go on repeatedly applying the intermediate value theorem, and that we shall call it as a bisection method. Now what we really mean is the root is lying between a0 and b0, therefore the product of these ordinates f of a0 f of b0 is less than 0. Now I bisect the interval and write this a1 is equal to a0 plus b0 minus a0 by 2. Here I may make a comment here, I had written the middle point of a0 b0 not as a0 plus b0 by 2, but I have use this as a0 plus b0 minus a0 by 2. Of course if I simplify it in our ordinary way, it will be a0 b0, but if you are going to a computation with finite length, you can take a simple example of a 4-digit number and then two 4-digit numbers and then find out what will be a0 plus b0 by 2 and what will be a0 plus b0 minus a0 by 2. This value is going to be much more accurate than taking a0 plus b0 by 2. So when you are doing finite arithmetic with a length is very small, then a0 plus b0 by 2 is an inferior approximation, inferior value compared to this one. Therefore I would prefer to use both, since even though mathematically both are equivalent, but for computation purposes I would take the middle point of the interval a0 b0 as this particular formula. Now when once I bisect it, I have now got two intervals a0 and a1 or a1 and b0. If f of a1 is not equal to 0, of course if f of a1 is 0, it is a root, by definition f of a1 is 0, it is a root. So if f of a1 is not 0, I will determine whether the root lies the interval a0 a1 a1 b0. Now that we can test immediately again by the intermediate value theorem. Therefore what I can do now here is I can test if f a0 f a1 is less than 0. If it is so, then the root lies in this one, otherwise it is other. We do not have to test the other one because there are only two intervals for us. If it root does not lie in one, it lies in the other one. So I will test only the first one. If the root lies here, then the root is in the interval a0 a1, otherwise the root is in the other interval a1 and b0. Now we shall repeat this procedure until the required accuracy is obtained. Now there is something very interesting in this bisection method, and that is we are doing bisection that means the length of the interval is reduced by a factor of 2. So, each bisection reduces the length of the interval by a factor of 2. If after n bisections the length of the interval is reduced by a factor of 2 to the power of n. So, I am doing n times the repeated bisections. So, therefore, each time it is reduced by a factor of 2, 2, 2 square, 2 cubed, so on. So, the after n bisections the length of the interval is reduced by the factor of 2 to the power of n. That means, if I start say the interval as 0 to 10, then the next interval, let us hope the interval is in somewhere near 0. So, the next time we will have a 0 to 5, that is a factor of 2. Now, I divide by a factor of 2, that is 2.5, 0 and 2.5. So, it is now reduced a factor of 2 square. So, each bisection will reduce by a factor of 2, so that after n bisections it is reduced by a factor of 2 to the power of n. Now, let us say that an error tolerance is given. So, an accuracy is given to us. I need what we really want to say here is that if I give you prescribe a tolerance of 6 plus accuracy or 8 plus accuracy, can you tell the number of bisections that is required? That means, what is the total number of bisections that would be required here? It is possible for us to do that in this case. Let us see this. Now, after n bisections, the length of the interval is reduced by a factor of 2 to the power of n. Therefore, the length of the interval is b naught minus a naught, and this length of the interval b naught minus a naught divided by 2 to the power of n is the current interval. After n bisections, this is the length of this interval after n bisections, and I want this length of the interval less than epsilon. Let us suppose finally I say that the root lies between 0.156 and 0.156525. So, these two are agreeing to the 3 decimal places. So, we are finally going to locate the root in the interval in which the a naught and b naught, the difference between them is less than given accuracy epsilon. So, this is the quantity that we have, that is the length of the final interval is less than epsilon. Now, once this is given, I want to, because here b naught is known, a naught is known, epsilon is known. So, I can determine n from here. So, I will take the logarithm on both sides. This logarithm of b naught minus a naught minus logarithm of 2 to the power of n is less than logarithm of epsilon, and then solve from here for n. I take this, keep it over here, write this as minus n times logarithm of 2 less than log of epsilon. Then I bring log of epsilon to this side, n log 2 to the right side and write down what is the value of n. N is greater than 1 upon logarithm of 2 logarithm of b naught minus a naught minus logarithm of epsilon. So, this is the n is the number of iterations that is required. So, what this states is I need a minimum of this many iterations, whatever the digit the nearest integer that we have here. I take the nearest integer and then say that this is the number of bisection iterations that will be required to get this accuracy of epsilon. Now, there is something very interesting, and that is the first thing is that the right hand side, okay, will come back to the slide again. The right hand side gives the minimum number of iterations required, because we are saying n is greater than, this one. So, this tells us that this is the minimum number of iterations that is required for this one, but usually that is the exact number of iterations also, because depending on the integer which you are going to round off, the integer, if you round it off to the next integer, then that will be the required one. Now, the most important observation that would be here is that in the testing this bisection, we are testing on the sign of f of a naught, f of b naught. We are not actually using the value. Let us say the value is f is minus 256.4. So, we are taking the sign as negative. But if the, let us take another function f(x) whose value is minus 3, but again we are taking the sign as minus. Therefore, whatever we have discussed does not depend on the value of f(x), it depends only on the sign, whether the sign is positive or the sign is negative. Therefore, all computations use the sign of f(x) at a point and not its value. Hence, this result is true for all f(x) is 0. As long as f(x) is negative, the result is same. Therefore, it is independent of a given function. Therefore, there are two things that happens. One is the result that you have just now noted is true for all fx. This result is not for a single function fx. This result is true for all functions, whatever be the function that we are considering. And secondly, since we are not using the value of the function, we are using only the signs, the method can never fail, because we are always locating the root in an interval a naught b naught. Therefore, the method can never fail. Therefore, bisection method, the question of failure does not arise. But if that is so, we do not need any other method, but the method is very slow. In a sense, it is slow. You start with a big interval, say 0 to some 50, and then you finally you may have to do about 50-40 iterations to get the required accuracy of, or maybe more than that, to get an accuracy of 6 decimal places. Therefore, it is for this reason that we need a better numerical method which gives the solution much more faster, but it can never fail. Therefore, initially when you are starting the iteration procedure, one can adopt a bisection method so that we are sure that you are getting an interval in which the root lies. Then we can jump from bisection method to any other method which will converge very fast compared to the bisection method. Now let us look at this again, and then just see for a typical example what will be the number of iterations that will be required. Let us take an example like this. Let us say that the root lies between 0 and 1. I have taken simple because in this case some of the things become 0 easy. A naught b naught, let us take 0 to 1. Therefore, n would be greater than I am just put it here. I am just substituting the, I just want to substitute a naught b naught over here. So, I have got here n greater than 1 upon logarithm of 2 logarithm of 1 minus 0 minus logarithm of epsilon. So that this actually goes off for me. It is easy to look at what is the values here, minus logarithm of epsilon divided by logarithm of 2. Then I would give the values for epsilon the accuracy that we want in a particular problem, 10 to the power of minus 2. When once I put 10 to the power of minus 2, I can take this as minus 2 outside, I can take it is 2 times logarithm of 10 divided by logarithm of 2, and then round off to the next digit, the integer. So, I will have 7 iterations. If I take 10 to the power of minus 3, I get 10 iterations, 10 to the power of minus 4 I have got 14 iterations. Similarly, I can construct for any other given epsilon. Now, if this interval was not 0 1, if this interval is say 0 to 20 you have taken, or 0 to 15, these number of iterations are going to increase further, because this number is going to be much larger. Because of that reason, even though it does not fail any time, still it is a very slow iterative method. Now let us just illustrate on a simple example. Find the real root of x cubed minus 5 is 0. Now I would first of all locate an interval of length unity. Let take the interval of length as 1. So f of 0 is minus 5, f of 1 is minus 4, f of 2 is 3. Therefore I find f1 into f2, they are of opposite signs, therefore it is negative. Therefore I would say that the root is in the interval 1 2. Now when once I locate this interval that it is lying in 1 and 2, I can go for the bisection and then say what will be the next interval in which the root lies. Now the midpoint of 1 and 2 we are taking it as 3 by 2, then I will find out the value of f 3 by 2 and the value is 27 by 8 minus 5, therefore it is less than 0. Now I test whether the root lies between 3 by 2 2, because we have taken the interval as 1 and 2. So the either it should lie between 1 and 3 by 2 or it should lie in 3 by 2 2. Now I find f 3 by 2 f of 2 negative, therefore root is minus 3 by 2 and 2. Sorry. Now I take the midpoint of 3 by 2 and 2, I get 7 by 4. Now again I find evaluate what is f of 7 by 4, f of 7 by 4, this x cubed minus 5, 343 by 64 minus 5 greater than 0. Product f 3 by 2 and f 7 by 4 is less than 0, therefore root is in 3 by 2 7 by 4. So now I can proceed on each time bisecting it and get the interval. The procedure would stop when the difference between these two is less than the given epsilon. Until that time the iteration shall proceed on. The computational cost, because when we are going to discuss the other methods, we would like to discuss the computational cost between different methods and then say which is taking less amount of computer time, so that the maximum that is time that is taken here is in computation of fx, because fx is a complicated function. So the computational cost, major cost is on computation of fx. It is not in a one extra division you are doing or extra addition you are doing. The whole cost will be based on the evaluation of fx. Therefore, we can say the computational cost for bisection is one evaluation of f, because each iteration will requires evaluation of one of the values of the function. So the computational cost for this is one evaluation of a function fx. Yes.
So if the number of roots are greater than 1, then suppose 3 or 5 within that interval, so this.
Yes. Suppose that there are 3 roots in an interval, say the interval 1 comma 2. Therefore, f of 1 into f of 2 is less than 0. Let us assume that the roots are 1, 1.2 and 1.3. If we bisect the interval 1 comma 2, we get the intervals 1, 1.5 and 1.5 comma 2. We find f of 1 into f of 1.5 is less than 0. Therefore, there is one root or 3 roots in the interval 1 comma 1.5. There is no root in 1.5 comma 2, since f of 1.5 into f of 2 is greater than 0. Now bisect the interval 1 comma 1.5. We get the intervals 1 comma 1.25 and 1.25 comma 1.5. Since f of 1.25 into f of 1.5 is less than 0, there is at least one root in it. The root 1.3 lies in it. But f of 1.25 into f of 1.5 will be greater than 0, since even number of roots cannot be captured by intermediate value theorem. However, if we bisect the interval 1 comma 1.25, then we get the intervals 1 comma 1.125 and 1.125 comma 1.25. Now f of 1 into f of 1.25 is less than 0, hence at least one root lies in it. In the present case, the root 1.1 lies in it. Again, f of 1.125 into f of 1.25 is less than 0. Hence, there is a root in the interval 1.125 comma 1.25. The root 1.2 lies in it. Now now we would like to move on to how to get the method better than the bisection methods. One is the methods based on the first degree equation to solve fx is equal to 0. Now let me see what is the concept behind this one. Now if you draw the graph of, let us just look at the graph of fx. This is the graph of y is equal to fx. This is our root that is required. Now if we know that if you are given any curve and I take any point on the curve, in the neighborhood of this particular point on the curve can always be approximated by straight line. If an infinitesimal segment of curve can be replaced by straight line. But now what I will do is, since I may not be able to get infinitesimal length on the curve, I will take a straight line as an approximation to the curve in the neighborhood of this, and then successively make this straight line become a real straight line at the point xi. Therefore, in the neighborhood of an exact root, we approximate the curve by a straight line, and the straight line is of the form fx is equal to a naught x plus a1 is equal to 0. Now once I approximate the curve by a straight line, the root required is the intersection of the curve and the x axis. Now if I approximate the curve by the straight line, the approximation to the root is the intersection of this line with the x axis. That means if I just set y is equal to 0 here, I will get an extra approximation for this. Therefore, if I am able to approximate fx by this straight line, then I will have here x is equal to minus a1 upon a naught. That means I am just setting y is equal to 0, that is intersection of this line with the x axis. Therefore, I will simply get x is equal to minus a1 minus a naught. let me just go back to this one. Now we say that we have approximated the curve by this straight line. How do you approximate it by straight line? How do you get the values of A0 and A1? Now we can get different methods by following different procedures to find the values of the constants A0 and A1, and these give us number of methods. The first method that we shall take is a secant or a chord method. What is a secant method is, I take any two approximations to the root, xk minus 1 xk be two approximations to the root, any two approximations. We are not saying that the root lies between xk xk minus 1, but it is, say if a root is 1.2, I may take 0.5 0.8 as approximation to the root. So there are any two approximations to the given root. Then what I do is I will take the point on the curve, I will take the corresponding points on the curve. We denote f of xk minus 1 by f suffix xk minus 1, f of xk is f of k. Now if I take this as the approximation, then I know xk minus 1 fk minus 1 is a point on the curve, xk fk is also a point on the curve, but we have just now approximated, just I will take out this slide once more, we approximated fx by this. That means these points that we have taken, they are all on this line, therefore these points would satisfy this particular equation. So I can substitute xk minus 1 fk minus 1 in the equation of the line to produce fk minus 1 is a0 xk minus 1 plus a1, f of k is a0 xk plus a1. I have got two equations, linear equations for solving a0 and a1. I can just solve, I subtract the two, get a1, and then substitute for a0, I get the value, other value. So if I subtract these two equations, what I would get to is, this is fk minus fk minus 1, a1 cancels, a0 into xk minus xk minus 1, and hence a0 is solved, a0 is fk minus 1 by xk minus xk minus 1. When once I solve for a0, I can determine a1 from any one of or either of these two equations. If I take this equation, I can write a1 is equal to f of k minus a0 xk. Now I have determined a0 and a1, and the root that we have said is x is equal to minus a1 upon a0 is the required root. So I will substitute the values of a1 a0 in x. Therefore the next approximation, I found out a1. Now I will write down the next approximation, that is substituting in this xk plus 1 is minus a1 upon a0. This is a1 is fk minus a0 xk, and I dividing by a0, I will divide it, first I will take this term xk minus fk upon a0. Now substitute the value of a0, a0 is fk minus fk minus 1, xk minus xk minus 1. Now this is the required formula, which we shall call as a secant method or the chord method. However, we can also simplify this, that is multiply these two and simplify further and write like this. So I just multiply these two, that is xk fk minus x suffix k fk minus 1 minus multiply these two xk fk xk minus 1 into fk, and therefore this gives us xk plus 1 is these two cancel off xk fk, and I would get here xk minus 1 fk minus this divide by this. So this is called the secant method, and we can use either of these two forms. I can use the form 2 or form 3 to get the next iteration starting from an initial value x0. As I said, the x0 is obtained either from the intermediate value theorem or through the bisection procedure we obtained, but we can use any one of these two forms. Sometimes this is convenient for error analysis. 2 is two is very convenient. We shall see in the next lecture how these two are useful in doing this procedure. Now the very important thing to note here is this. Let me just keep this over here. We made starting we said that xk minus 1 xk are any two approximations to the root. We did not ask or require that the root should lie between xk minus 1. The root need not lie in xk minus 1 xk. The method gives convergence to the root from one side of the root. The convergence for the secant method is always from one side of the root. Even if I start that the root lies, so let us suppose the root was 1.5 and we have taken the root lies between 0 and 3. The root lies between this. This iteration will take one or two iterations to jump to one side of the root. So it will go either to 1.5 to 3 or it will go from 0 to 1.5 side and then start converging from one side only. That means if we are using secant method and if you start with a root lying in an interval, you would lose one or two iterations so that the convergence will come from only one side. The convergence is always from one side for the secant method. Now the cost of the computation will be at each iteration we need one function evaluation fx plus 1, which is the major cost in applying this method. Again it is the cost is the same as bisection. Here also we are having only one function evaluation, there also we have one function evaluation. Therefore the cost is the same but the procedure is different, but here of course we can count for each iteration. There are two multiplications here and there are two subtractions here and one division here. So you have got the other operations also for each iteration, we will be able to tell over here. Okay, I think we would stop for this today.